Hello and welcome to another lecture for Introduction to Astronomy. Today's topics will be the Moon and Mercury. In this lecture, we will talk about Mercury and its visual and compositional characteristics, as well as talking about the Moon. So in the last lecture, we talked a little bit about what makes the Earth so special, and part of what makes the Earth special is the Moon. We'll also talk about early lunar studies and the Apollo missions to the Moon. And this will give us this helps give us a timeline of lunar history, especially because we are able to bring back samples, and so we know a little bit about lunar geology and some of the lunar timeline. We also will talk about how impact craters form and can be used for dating terrestrial objects. We'll also go over the hypothesized origins of the moon because the exact way that the moon formed is one of the open questions in astronomy. Then we also will move on to Mercury with its unusual composition and also some hypothesized origins for it. So you might be wondering, why are we talking about the moon and Mercury? Well, when we use our comparative planetology and we look amongst the terrestrial objects, the moon and Mercury are actually by far the most similar. So they have some pretty similar visual characteristics in that they both have lots of impact craters from heavy bombardment and violent collisions in their past that shape their surfaces. And they're both relatively small, with solid surfaces composed of rocks and silicates, which is similar to all terrestrial objects, but they are also both geologically dead and have very tenuous to almost no atmosphere whatsoever. But they are drastically different in compositions. So let's go over the physical characteristics of the Moon and Mercury. They're similar in size with comparative diameters, with the Moon having a diameter of 3,476 kilometers and Mercury having a diameter of 4,878 kilometers. They, however, have very different masses. This gives them very different densities overall, and this also means that they have different gravitational field strengths on their surfaces, which means that you would have to have different escape velocities to get off of them, respectively. You would need to be traveling much faster to have an escape velocity for Mercury than you would the Moon. So, this difference in density, but with similar volumes, implies that the compositions under their surfaces are very different, with Mercury being composed of much heavier stuff than the Moon. Let's go explore the Moon. Of all of the celestial objects, we know the most about the moon because we have actually sent humans to touch the surface of it. Most of our lunar knowledge comes from the US Apollo program, which ran through the 60s and the 70s. But in particular, we got a lot of knowledge from the Apollo 8 and through 17 missions, which ran from 1968 to 1972. The most notable of all of these is the Apollo 11 mission, which was the first mission to land humans on the moon. Neil Armstrong was the first man to step on the moon with his famous quote, "One small step for mankind, one small step for man, one giant leap for mankind." We also have Eugene Buzz Aldrin and Michael Collins. Hey, other Michael. Since Apollo 11, 12 other astronauts have landed on the moon, with the last Apollo mission, Apollo 17, having a geologist, Harrison Jack Schmitt, being the last person to step on the moon, most recently. Jack Schmitt is also credited with taking one of the most famous photos of the Earth, and this was taken from the moon's surface, and this photo is called the Blue Marble. Also, he collected a very interesting sample of the lunar surface because this sample provides conclusive evidence that the moon once possessed a magnetic field. The Apollo missions had a lot of objectives, and their success is considered one of the most impressive feats in modern science. So they had to collect nearly 400 kilograms of samples from the moon's surface, little bits of dust, big rocks, and everything in between for laboratory analysis, which helped confirm a lot of our understanding of how the moon was made up and gave us some insight into its origins. They also deployed some packages on the moon surface called the Apollo Lunar Surface Experiment Packages, which collected data and had to operate for several years after each mission. Also, in the Apollo missions, besides landing on the surface, there would be an orbiting command module equipped with a lot of scientific instruments, specifically those for photography and analysis of the lunar surface while in orbit around the moon. But despite so many positive results and a lot of public interest due to political and economic pressures, a lot of the funding was cut, and so future missions to the moon stopped happening. But this scientific interest never stopped, and there have still been spacecraft sent by various other nations and space agencies to the moon since the Apollo missions, but we have not sent another human there since. Those 400 kilograms of lunar surface samples gave scientists a lot to look at. So they were shocked to find that the moon is not composed of exactly the same material as the Earth. In fact, the moon's overall density, on average, is about 3.3 grams per cubic centimeter, while the Earth's is nearly 5.5 grams per cubic centimeter. They did find that the moon is composed almost entirely of silicate rock with very little amounts of irons or other heavy metals. And so it's almost as if the moon were made up of the silicates from the Earth's crust and mantle. This gives some really interesting clues into how the moon may have formed. They also found that the material from the moon's surface was very devoid of any water or other like volatile materials. And this makes sense because they would have easily evaporated due to a lack of an atmosphere on the moon. But recently, some water has been found in the form of ice in permanently shadowed craters near the lunar poles. And this would be very useful for future missions in exploring our solar system because ice is not only water for humans to consume because we need water, but water is made up of hydrogen and oxygen, which are two of the main components in rocket fuel. So this would be very useful if we could set up ways to collect that ice on the moon's surface. You might be wondering, how did that get there if we just said that any water in those surface samples had evaporated? Well, it's presumed that this ice was carried there by the comets and asteroids that collided with the moon, because many comets are composed of lots of ices, and in fact, asteroids also have quite a bit of ice in them as well. We're all familiar with the moon. We've all seen it in various phases during the night, but we may not have known what exactly we're looking at and had the right language to describe it. So the moon is covered in impact craters and darkened areas of different sizes. Early astronomers thought, when I say early, I think I must mean very early, postulated that these features were continents and oceans and that the moon could be home for life just like Earth. Now we know a little bit more about this. We know that the moon has very little atmosphere, if none at all, and we know that the moon does not have life on it. So the dark areas on the lunar surface were believed to be seas in the past, and so were called mare in Latin, which is still what we describe them as. We call them mare, whereas the land areas were unnamed. The prominent craters on the moon's surface are named after some early astronomers. There, for instance, there are the Copernicus craters. We can see the Tycho crater marked on the image on the right. There's also Kepler crater. And craters have very unique structures when compared to other impacts. The craters on the moon have very unique structures when compared to other impact craters on Earth or on other terrestrial objects. This is primarily due to the moon's lack of geological activity or any protective atmosphere. So this makes impacts on the moon unique among terrestrial objects. So the moon had a very violent history. After its layers differentiated, its surface solidified about 3.3 to 4.4 billion years ago. This is considerably long before the Earth's surface did. So 83% of the moon's surface consists of silicate rocks in the lunar highlands. These are low-density silicates, which solidified during the earliest parts of the cooling, and that resulted in more cratered regions in these highlands. So the highlands on the moon, the lunar highlands, are very hilly, cratered regions, kind of like the Scottish Highlands are very hilly regions in Scotland. There's also mountainous substructures in the lunar highlands that have been heavily eroded, just like the oldest mountain ranges on the Earth. However, this erosion was due to debris from impact cratering, which created smoother features over time. Erosion on Earth happens differently than erosion on the moon. On the moon, the erosion is due to a lot of this very fine silicate raining back down after impacts happen. And so the other 17% of the moon's surface that is facing the Earth is referred to as the maria. The maria is less cratered and is composed mostly of basalts. And this is due to a history of volcanic activity. This is volcanic activity in the distant past. So, volcanic lava in the maria gradually filled large impact basins during the various early parts of the lunar history, and much of the first billion years of lunar geologic activity has been lost due to this volcanic lava flow. However, the volcanism on the moon halted about 3.3 billion years ago after the moon's interior cooled down, after it lost its primordial heat. Surface dynamics of the moon are dominated by heavy bombardments now that the moon lacks geologic activity. And this has resulted in a surface covered in very fine-grained rock fragments. These rock fragments are very porous and loosely packed dust, and it covers much of the uppermost layers of the moon's surface, and this makes it very meddlesome for terrestrial equipment and probing devices. It's very difficult to work with the lunar dust. This dust was created over long periods of impacts along the surface, during which fragments and bits of debris were kicked up and then rained back down over the surface. And over billions of years, these impact events and the bombardment of the moon's surface resulted in a very fine-grained surface material. So in addition to not having an atmosphere, it also has very high surface very high surface temperature fluctuations throughout the day. And this is because of it not having an atmosphere. And this is despite being the same distance, roughly the same distance from the sun as the Earth. So the moon's surface temperature varies greatly, with day being about 100 Celsius in some parts, which is equivalent to 212 degrees Fahrenheit, down to minus 173 degrees Celsius at night, or equivalently minus 279 degrees Fahrenheit. And this is because there is not an atmosphere to trap in that heat, so without the daylight, at nighttime on the moon, it gets very cold because that heat just evaporates out into space. It radiates out into space, not evaporates, radiates out into space. This may come as a bit of a surprise, though, that it wasn't until the early 20th century that scientists began to recognize that lunar craters were actually the result of impacts and not just very large volcanoes. So we can see on this image on the left that craters, when viewed from far away, could look very similar to volcanoes. However, the terrestrial volcanoes that we know have very much smaller openings, very smaller calderas compared to the size of lunar craters. And also, lunar craters have a bit of a bump in the middle due to the fact of it being resulting from an impact. So in the 1890s, Grove K. Gilbert noticed that the lunar craters were different in structure from the volcanic craters here on Earth. And so he suggested that the results he suggested that these lunar craters must be the result of impacts due to their shape and not volcanoes. But his hypothesis wasn't accepted at the time or even during his own lifetime. It took until after he died for this idea to really catch on and his hypothesis to really gain the evidence that it needed. And the reason being that lunar craters are circular and not oval, and they believed that impacts would scrape out an oval onto the surface of a terrestrial object instead of a circle. We now know today that the circular shape of craters is due to the escape velocity of the moon. So the escape velocity is equivalent to the minimum velocity a projectile will have when impacting the surface. The moon's escape velocity is 2.4 kilometers per second, 2.4 kilometers per second, and this adds to the initial velocity of the projectile, which results in an explosion that evacuates a large volume of material in a perfect symmetrically. So this would give it that circular crater shape, and the projectile then penetrates a depth that is 2 to 3 times the projectile's diameter, and it excavates a crater that is at least 10 to 15 times in diameter of the width of the projectile. The central cavity of an impact is going to be initially kind of bowl-shaped, but because of the lunar dust and debris, the cavity gets filled in by rebound. This is material that then falls back down from the initial impact, and this produces a flat floor along the crater and sometimes even a central peak. Crater rims are turned slightly by the force, and the surrounding rim is often what we call an ejecta blanket of material that is thrown off by the impact and creates a rough hilly region and sometimes even secondary craters around it. There can also be very large rays emanating out from these impact sites, and this is from streams of ejecta falling back down around the crater. So this gives craters on the moon very unique shapes and dynamics, and we can see them every night when we look up at the moon because the moon is just absolutely covered in these. In fact, the Tycho crater has some of these rays that we can see. We can actually use craters to help determine the age of the moon. So we can estimate the relative age of terrestrial objects by counting the number of impact craters on their surface. So objects that formed a long time ago will have had more time to be impacted and thus have more craters on their surface, whereas objects that formed more recently will have less craters. So using the moon, it's actually a very good example of this because it ceased geologic activity such a long time ago, and thus preserving those craters. So scientists calculated based on the craters in the Maria that the moon is several billion years old. And this is consistent with the radioactive dating from samples taken from there during the Apollo missions, which found that these regions were 3.3 to 3.8 billion years old. This agreement between two independent measurements really confirms this estimation that the moon is very old and is a great method, or it's a great example of using the scientific method. Scientists can also use these studies to infer that the early periods of the solar system were far more violent. So when we look at the impact craters in the lunar highlands, they appear to be nearly 38 billion years old using these counting methods of relative age. And this is far older than the solar system and is in fact far older than we know that the age of the universe. This tells us that the highlands actually preserved a lot of these periods of heavy bombardment because the bombardment was not uniform over time. Much of the impacting happened during a very short period, which makes sense with a very violent early solar system. And so I just really want to stress that the moon is not 38 billion years old. It only appears this way when we use relative aging, when we estimate its relative age from impact craters. Now that we know a lot about the moon's surface and its composition, and we know some of its history, and we've inferred the history of the early solar system from the moon, we can now hypothesize on how the moon may have formed. So there are several hypotheses for the origin of the moon, and some of the early ones are known as the fission theory. And this is that the moon was once a part of the Earth, but somehow during their development got separated, and then they developed as two separate bodies together. There's also the sister theory, and this is that the moon and the Earth formed together, but as two independent bodies, that they never fissioned off, but were just there next to each other, forming independently. There's also the capture theory, that the moon was formed elsewhere in the solar system and then somehow gravitationally captured into a perfect geosynchronous orbit with the Earth. Each one of these theories, though, has their own problems which cannot be solved. Fission, its problem is that modern calculations show that a spontaneous fission between two bodies of that size is impossible due to the gravitational force between objects of such large similar masses and such large masses. There's also the problem with the sister theory, and this is from samples show that the moon is not made up of as much similar stuff as the Earth. So if they formed together, then they would be much more similar in their composition. And the capture theory is the easiest to dispute because Newton's laws imply that there is no way that an object as large as the moon could be captured by the Earth's gravitational field without slowing down as it approaches. And then a captured object would be way more as eccentric than we see the circular orbit that the moon is in. This leads us to our fourth hypothesis on the origin of the moon. In an attempt to resolve the faults of the previous three, scientists came up with the giant impact hypothesis. And so this suggests that during the early period of the Earth's history, the Earth was struck by a large object that was roughly 1/10 of the Earth's mass, and then some of the Earth's mass and the debris from this object were ejected into space, which formed a planetary ring, which then ultimately condensed into the moon. And so simulations of this event are surprisingly consistent with what we've observed, although we don't have a possible way to confirm the giant impact hypothesis. And so, despite this lack of concrete proof, this model better explains the major contradictions of the previous hypotheses, and it explains the chemical evidence that suggests why the moon is composed primarily of rock and mantle elements and is devoid of the metals which were condensed down to the Earth's core during the Earth formation when the Earth layers differentiated. Furthermore, the water and other volatile elements that may have been present on the moon were lost during this heated phase that followed such a severe impact, and so this would explain the lack of these materials on the moon. So now that we know a lot about the moon, let's look at another rocky cratered neighbor of the Earth that has no atmosphere. Let's look at Mercury. Since Mercury is the closest planet to the Sun, it has the shortest orbital period, with a Mercury year being equivalent to only 88 Earth days. And so it was nicknamed Mercury. It was named Mercury for the Roman messenger of the gods who had to be very fast. However, since Mercury is the closest to the Sun, it is very difficult to observe in the night sky and is best seen when it is at the furthest point in its eccentric orbit, when it is at aphelion. What's really surprising about Mercury and its composition is that it is very dense. Mercury is only 36% of the Earth's radius and size, but they have nearly the same density at 5.4 grams per cubic centimeter, which would imply that Mercury must be composed of very heavy elements, much more so than the moon. And models suggest that Mercury's core must be primarily iron and nickel, and this would account for 60% of the planet's mass. So you can think of Mercury actually as being a giant ball of metal with a rocky crust. Measurements by probes have found that Mercury does actually have a magnetic field. So this suggests that at least some part of Mercury's interior and its core must still be liquid. Not much was known about Mercury's surface until 1974, when the Mariner 10 spacecraft, launched by the United States, passed by the planet and transmitted photos back to Earth. It was until 2004, with the Messenger spacecraft, that we got a much more detailed uh, view of Mercury's surface. We now know that Mercury's surface is very similar to the Moon, with lots of porous dust on there and many impact craters, but with a bit more temperature extreme on the hot side, with temperatures on Mercury in the hottest parts reaching 806 degrees Fahrenheit, with the colder parts on Mercury actually being minus 274 degrees Fahrenheit. Mercury has a huge range in temperatures. The Messenger spacecraft was also able to confirm that Mercury had past geologic activity, although it is no longer geologically active. But what may be most unexpected is that there is actually water ice in deep in the craters near the poles of Mercury. And in that ice, they have found organic, meaning carbon-rich compounds in that ice. That's that's pretty cool. That's on Mercury, somewhere you would not expect. Not only would you not expect there to be water, but organic compounds on such a planet with such hot temperatures. Being able to find that really is really exciting. However, unlike Earth, Mercury has no evidence of plate tectonics, which means it actually is probably experiencing some very strange geological phenomenon, because when we see these long scrapes along its surface, like on the image on the lower right, this suggests that Mercury may have actually shrunk in size in the past 4 billion years. So very strange geology going on Mercury. Trying to understand how Mercury formed is a very difficult topic to study, because Mercury's unusually high density and high metal composition makes it very different from these other terrestrial objects. So astronomers believe that Mercury should have originated with a similar ratio of silicates to metals as the other terrestrial planets. So how did Mercury lose all of those rocky materials and become mostly metals? Well, the leading hypothesis is that Mercury has just been bombarded from its very beginning. That meant a lot of this rocky material was torn away over time from many giant impact events, which left Mercury with very little rock around its crust. And this is consistent with our current understanding that the early solar system was extremely chaotic, and it would have been even more so closer to the sun, which is where Mercury is located. And so this fragmentation reshaped Mercury into a metal ball that is mostly just coated in rocks. But we do know there's a little bit of ice now in those craters near the poles. And Mercury really serves as a testimony to how crazy the early solar system was during planetary formation. This concludes the lecture.